This is the Vic Academy, and today we are looking at characteristic and minimal polynomial worked examples. We want now to revisit what we have already looked at for various topics, and if you have not come across them, kindly look previous topics and we'll be able to see what you have done. If you have any question about any of the topic, kindly leave a comment and we'll be grateful to answer you. Okay, now we want to look at some of an example, worked example here, and we want to find both characteristic polynomial and a polynomial and a minimal polynomial. So we want to find the characteristics. That's what I'm using as x. That's my polynomial, and also minimal polynomial. So basically, if you have a given matrix A, which is given as 1, -3, 3, positive 3, 3, -5, 3, 6, -6, and 4, and we want to get the determinant of these to get the characteristic polynomial for this matrix, which is a 3 by 3 square matrix. We need to get the determinant of xi minus a. That is basically the characteristic polynomial of matrix A in terms of x. So we know that the determinant of this will be same as x minus 1, 3, -2, and -3, x plus 5, -3, -6, 6, x minus 4. So we are getting that determinant, and if we want to get the determinant, remember what we normally do, we multiply the main diagonals, we add the lower part, that multiply product, and we again lower this part. So that if you do this, you'll find get the determinant of this, you get that our p x is actually x power 3 minus 12x minus 16. So that is actually a characteristic polynomial. So next, we want to look at minimal polynomial. From the claims that we had looked at in the previous tutorial, is that the minimal polynomials defines the polynomial, characteristic polynomial. So it's like we work for the roots of this polynomial, this characteristic polynomial, and we will find that the roots, which we normally call the eigenvalues, are actually x or lambdas being the repeated root, and this. So remember, this is just using the methods and which we normally use to solve polynomials. And now it will mean that the only combined possibilities that we can become minimal polynomials in this are x, the polynomials x plus 2, because this x plus 2 subdivides or divides fully without a remainder the characteristic polynomial. Again, x minus 4, because again this x minus 4 divides characteristic polynomial fully without a remainder. And again, you can see this, if you check this will also this squared. Why are we saying that squared? Because it's from here. Repeated polynomials, repeated roots are squared, and again the polynomial, the characteristic polynomial itself. So these are the possible minimal polynomials of A. These are possible minimal polynomials of A. So, those are the possible minimal polynomials of A. But remember, which one is fully minimal? Which one, if you multiply, you get 0? You'll find that that one will be actually the simple combination of these. So that will be now the final minimal polynomial for A. X, so m of x is actually x plus 2 plus x minus 4. Because remember, the minimal polynomials should mean that this is equal to 0. So we are just using the possibility and see the combination that will give us this being equal to 0. If we get that, then that becomes the minimal polynomial. The others, if you look at other combinations there, like x plus squared, x plus 2 squared, then you can see over here that one is not giving us 0. Not give us 0, to not be equal to 0. Okay. So what we need to note here is that if we have px, which is the polynomial, characteristic polynomial, being equal to x minus the engineer value 1 to power k1 kx minus lambda 2 k2, that way the k1s and the k2s that way are the what we call the simplest multiplicities. So the eigenvalues of lambda 1, lambda 2, lambda, all that one are of multiplicities of k1, k2 to k so on respectively. And then if you have a minimal polynomial mx, which is actually x minus lambda 1 say to power r1, x minus the 2 to R2 that way, you'll find that for r's which lies between for this one, for r1s being lying between 1 and ki, so it can be more than the upper limit, can be more than the one for characteristic polynomial. Then you'll see that every factor of px will be also a factor of mx of x. So every factor of the polynomial characteristics is also a factor of the minimal polynomial with the multiplicity either less or equal to that of the characteristic polynomial. So this R1 will be either equal or less than k. It will be. So this tells us that the minimal polynomial, if we could pose a question like, what does a minimal polynomial tell us about a matrix? The minimal polynomial tells us that if that minimal polynomial has no repeated roots, then that matrix is diagonalizable. So if you find that that's a particular polynomial, minimal polynomial has no repeated factors, then of course that will be diagonal. And the vice versa is true, that if the minimal polynomial has repeated factors, then it automatically tells us that that A is not diagonalizable. Okay, so we need to note this, which is very important, that every square matrix is similar to upper triangular matrix. So if you have a particular square matrix A n by n, this one is similar to upper triangular matrix whose diagonal entries are the eigenvalues. So we are having T, which is of course it's a upper triangular matrix whose diagonal entries are eigenvalues, and they are counted up to multiplicities. So H1 that way up to the last multiplicity. So this is very key. So you have to subscribe and also share with your friends, because the next topic that I'll be looking at is Jordan canonical forms. Jordan canonical forms are basically a makeup of what we have discussed here about minimal polynomial. What does it mean in a given characteristic polynomial or in a given matrix? So we have seen that in case your factors are not repeating, then that matrix, but if you find factors are repeating, then automatically that matrix is not diagonalizable. And again, the minimal polynomial will have factors which will have multiplicities which are less or equal to the characteristic polynomial. So those points are very key to note as we proceed to Jordan canonical forms. Okay, so if you have not shared to your friends, or share this, and